Okay, everybody. So, as you can see, I'm starting this video in this video series, because I think it'll have 2 or 3 parts to it, with a question. All right. And it's only because this concept comes up in all the other questions that we're going to deal with. Uh, this is not the main idea of the lesson, but it's just something we have to get out of the way and make sure that we can all agree about. Okay. All right, so that question is, what is a solid of revolution? So here's the setup for that. Say you have some area, some region of the XY plane, all right? And it may be given to you in picture form, it may be given to you by equations, or, I guess lots of different ways, but let's say that it's given to you like this. So I'll describe it first, and you can pretend you don't see that picture. And it says, consider the area bound by these 3 lines. The line y is equal to 2x, which is right here. The line x is equal to 3, which is a vertical line right there. And the line y is equal to 0, which is the same thing as the x-axis. Now, if you intersected those 3 things, the space they would contain would be this triangular space right there. Okay? All right, so now to the idea of a solid of revolution. Suppose you took this triangular space right there, and you rotated it 360 degrees around the x-axis. What three-dimensional shape would you get? All right. If you're having trouble imagining that, imagine that this pencil is the x-axis, and I could get like a cardboard triangle, and I could glue it to my pencil. All right. And imagine that I could spin the pencil around so fast, which I can't do, but imagine that I could spin the pencil around so fast that it would create just a blur. What would that blur look like? It would look like a cone, all right? If I take this flat triangular region, rotate it 360 degrees around the x-axis so fast that it just creates this blur, this illusion of a three-dimensional object, that object would be a cone. All right, so we'll have to agree about that, because if you don't have the imagination for three-dimensional shapes, then this particular lesson will be very hard. But if you don't have that good of an imagination about it, well, that's something we can work on, or you can ask me about. Anyway, so in fact, we would get a cone. We would get this particular cone. You see how the line y is equal to 2x and the vertical line x is equal to 3. They intersect each other at this point where x is 3 and y is 6, because y equals 2x, and 2 times 3 is 6. All right. So the specifics, the dimensions of the cone, are that it's going to have a radius of 6. Okay. Because that's formed by this aspect of it once we rotate it around and we get this cone right here. Okay, so I'll have a radius of 6 and it will have a height of 3. Now, do you see why that is? Do you see why I'm saying we'll get a cone of roughly this orientation? Radius, the circular radius, the radius of that circular opening will be 6 and the height will be 3. Okay. And it's called a solid of revolution because this flat thing, when revolved around the x-axis, becomes this three-dimensional solid thing. So we call them a solid of revolution for that reason. All right. Now, let's take a follow-up question. What our lesson is really going to be about is how do you calculate the volume of certain kinds of three-dimensional shapes. All right. So what is the volume of the solid of revolution above? So this one right here. So if you take this triangular region, you rotate it 360 degrees around the x-axis, and you will get this solid three-dimensional region or shape, okay? What is the volume of that? Well, it is a cone, and I'll give you a hint there. The volume of a cone is 1/3 times pi times the radius, and I mean the radius of this circular opening, okay, times its height, and that will be this aspect of it, all right? Even though you might think of the cone like that and say, well, that's its height. Well, okay, I'm turning it on its side, and I'm going to say that's the height. So, well, that's pretty easy to do. I gave you this hint, right? I told you the formula, so it shouldn't be too bad. Volume is 1/3 pi. Okay, so what's the radius is 6. Okay, so 6 squared, and then times the height, and we said the height was 3, so 3. And so I'll get 36 pi. The 3's will cancel out of that. So 36 pi. Okay. 36 pi what? Units of volume, all right? So I mean, it'd probably be good if I worked with the units. What if I told you that the x-axis was like each mark on the x-axis was in feet, and each mark on the y-axis was in feet. So like this was like some giant thing to scale, and this line was 3 feet over. And then this point right here where that line intersected this one, that was 6 feet upward in that direction. Then what would that number mean? It's volume, so it'd be cubic feet. All right, if we're using those units. So I'll say 36 pi feet to the 3rd power, cubic feet being a measure of volume. All right, now at this point, we got the basic idea out of the way. We need to tackle the general problem, all right, where, you know, this shape here doesn't necessarily lead to something we have a name for. Like that shape is called a cone, and there is a standard formula for its volume. If this shape was unusual here, we wouldn't have a name for the solid of revolution, and we wouldn't have a formula for it either. So we need to consider what would that happen. So I thought that I would give you some general instructions, okay? And in these instructions, you'll see like the basic setup or a basic description of the problem, as well as the instructions. So, okay, general instructions. How do you calculate the volume of a three-dimensional solid object that spans the x-axis from point A to point B? So here I drew this like it meant to be totally amorphous, but let's pretend that this is a potato, all right, as silly as that is. And it spans the x-axis, all right? So I've taken this thing, I've positioned it, and I'm going to say, well, okay, it starts at x is equal to A, and it ends at x is equal to B. That's its span along the x-axis. That's a 3D solid object. We'll pretend it's a potato, if that would help you. Okay, we need to consider the slices of it. All right, now here's what I mean. Imagine that I've got my cutting board, and I for some silly reason, drew the y and the x-axis on it. And I get my knife, and I cut this potato perpendicular right there. I cut this very thin slice, okay? That's what that circle represents. It's like I want to cut get my knife perpendicular to the x-axis, all right? And I want to cut like so. That's called a cross-section, all right? And we need to be able to do something called find the function a of x, which is the area of the cross-section. So can you imagine if I had this potato, we're going to imagine that's what it is for now, and I chopped it up into slices. What shape would the slices be? They would all be circles, okay? Or they'd be, if they weren't perfect circles, they'd be, we would say, well, they're circular enough to call them circles. But if I chop it up into tiny little slices up and down, then every cross-section would be a circle, and I need a function that tells you the area of the cross-sections all the way through. If I chop this up into little slices or cross-sections, the circles in the middle would be the biggest, and towards the end they would taper down a little bit smaller. It'd be something like that, all right? I need some formula that tells you the area of any one of them, no matter where it is. A of x is the area of this slice, or it's a formula. It tells you the area of any of them, okay? Now that might be a little bit too abstract for you right now. You might really need to see some examples to understand that, but that's part of why we do the examples. Okay, so here are the instructions. Determine the shape of the cross-sections of your object. Cross-sections being that they're cut perpendicular to the x-axis. So if I had this shape and if it was a potato, all the cross-sections would be circular. That's the first thing. Second thing, determine the function a of x. It's a function that will calculate the area of the cross sections at any point on the x-axis because they're going to be different sizes at different places. We need a formula to calculate it no matter where it is. Remember, I said for this potato, the circular cross sections, well, they're all going to be circular, but they'll be bigger in the middle. They'll taper a little smaller to the ends. I need a function that tells you the size of the cross section no matter where it is. Now, that's probably the big hurdle, is figuring this thing out. If you can figure that out, then here's your integral that tells you the volume of the object. So you go from finding a formula that tells you the area of the cross sections to an integral that tells you the volume of the solid object. All right, so those are the instructions. Now, I just thought, whether or not you would consult these instructions every time you did a problem, it would be good to just put it all in one place. And, if you didn't like it, you can skip over it and just go to the problems. That's always my thinking with the videos. Anyway, let's do a problem. So suppose we want to calculate the volume of the object formed by rotating this region right here about the x-axis. So that triangular region, again, I want to take something like that. I want to rotate it 360 degrees around the x-axis. Okay, calculate the volume of that. Well, to take the mystery out of it, where I don't know if at this point there is any mystery to you, but if I took this triangular space and I rotated it 360 degrees around the x-axis, I would get that cone, right? It would be like that. Now, what were the steps? What kind of cross sections is this going to have if I cut perpendicular? See that cone right there that's spanning the x-axis according to how that triangle spanned the x-axis? Chop it into little slices, little cross sections. What shape are they going to be? The shape of the cross sections is going to be circular. Okay? Cross sections as I am defining them. I'm defining the cross sections to be slices of the object perpendicular to the x-axis, like so. All right? Okay, so circular cross sections. 2, I need to find this thing called a of x. Okay, and what does a of x do? It tells you the area of any of the cross sections. Now, say we can agree that, yes, in fact, if you slice this into 100 tiny slices, they would all be circular. We'd probably agree about that. We could also agree that they'll all be different sizes. If you cut this into a bunch of tiny slices, they would all be circular. They'd be bigger over here, and then they would taper smaller over there. How are we going to get a formula that tells you the area of any of them, no matter where it is? Well, okay, let's go back up here and think a little bit about how rotating this gave rise to this, okay? Wouldn't, like, this particular aspect, see that line right there in red? Isn't that distance what gives rise to the radius over here? Because if like, say, right there, there's this circular cross section, then the radius of that circle came from, like, whatever, band or length is over here in this triangle, okay? So this is, in general, what gets you the radius. Okay, so just now let that sit for a second. Think about that. Now, since they're all circular, the area of the cross sections would, in general, be pi r squared, because that's how you find the radius of a circle, generally. And for this particular shape, how are you going to tell me how far that's what's going to get you the radius when you revolve it, okay? All right, that is what's going to give rise to that radius of this circular slice. But how do you tell me how big that is? Well, it's like depends on where you are. It's different sizes everywhere. I could draw a line here and say, well, that's the radius. That's smaller than this. I can draw a line here and that's the radius. What are you going to tell me the radius is? Well, in general, the radius is this vertical distance from the x-axis up to that line. Okay? And that distance is the y-coordinate of this point. And the y-coordinate of this point is 2 times the x-coordinate of the point. So the radius is going to be y, or it's going to be 2x. That's what we want. We want to say that it's 2x. So pi times 2x squared. Okay? 2x is the radius. You can't tell me the radius is a number. You can't say the radius is 4, because the radius is different sizes everywhere. It's going to have to be put in terms of x. Now, so the way this would work is you give me x, you tell me where you are on the x-axis, and then 2x is the radius of the circular cross-section at that spot. Okay? So we could try this out. We could say, what's the radius of this, the opening of the cone? Well, where is the opening on the x-axis? I guess it would be at 3, okay. So the radius there would be 2 times 3, that'd be 6. So this opening part right here, that part at the opening is a circle, and it has a radius of 6. So you tell me where you are on the x-axis, 2x is the radius, pi times 2x squared is the area of that circular cross-section. Okay, now let's multiply this out a little bit. We might as well square the 2x. The 2 and the x get squared, so we get 4 pi x squared. All right, now that's probably the hardest step. What was the last step? The last step to find the volume was the definite integral, where the lower and upper limits of integration were the span along the x-axis of the object. And so this object spans from 0 over to 3. So we want to go from 0 to 3. And then you put your a of x formula here. That's 4 pi x. 4 pi x squared. And then we work this integral the way you would work any integral. We get the antiderivative of 4 pi x squared. So that's going to be 4 pi x to the 3rd power over 3. And then we want to take that from 0 to 3. If we put 3 in, so we'll get 9 out of that times, so that's 36 pi. And then if I put 0 in, I won't get anything, so 36 pi is my answer. So that there is the volume of the cone, where it's in units to the 3rd power, feet to the 3rd power, centimeters. It depends on how you are making your measurements in the beginning. Okay. Now, when I put this problem on paper originally, I was hoping that you think that it sounded familiar. So this was the same problem that I started with. But when I started with this problem, I just wanted you to get the concept of a 3-dimensional shape and the concept of revolving. And I even, as a bonus, I said, well, can you tell me the volume of it? We got 36 pi. And then now here we're doing it with calculus, which is not nearly as natural, but here we're here to learn calculus. But here I did the same problem on the same shape with calculus of finding the volume of that cone. I got the same thing. Of course, 36 pi. There's only one answer, and it's 36 pi. But I wanted to show you that I could do it 2 ways and use that as a way to introduce all the concepts that you need to know for the lesson.